Hi, we're redesigning a hand drill for manufacturability and assembly as part of our 452 project. To start off, we took the hand drill from CAD from an online source, and based on our initial analysis, we were able to establish how many parts it has and what their purposes are. Based on some research, our primary customers are people in construction and manufacturing related businesses with secondary customers as hobbyist builders, leading to an overall production quantity of around 10 million hand drills per year. After that, we were able to decompose the drill into multiple sub-functions and subsequently associate these functions and individual components. Seeing the functions of these components as well as doing a basic BOM analysis allowed us to create a very basic quad chart classification that outlined all the different importance and cost across these parts. And from that, we chose to specifically focus on the drill axle and the left outer shell for later DfM analysis. Now, looking at the product family, we saw that the main difference between the needs of the customer groups was the ability to control torque, and we were able to look at a few key parts that act as modules for the torque control. These parts could easily be modified to reflect the functional difference, essentially through different attachment styles that promote the difference in use, such as with this torque ring here, modified to include the spacer together and connect to the drill itself, as well as some of these outer shell pieces that could be modified to incorporate that torque ring in a more solid way. And so, yeah, along that, we have some key interfaces that represent points of interchangeability for these modules as well as overall function. And in using that with the modules, that left us with two major assembly sequences across this product family and gave us a starting point for an actual design for assembly as well as manufacturing.
All right, so for our manual DFA, we chose the drill axle for our platform part and the left body shell for our module part. We chose the axle because we evaluated it being high cost and high functional performance from our quad chart. And it's also a simple part, so we can make useful changes without changing that part's functionality too much. We chose the left body shell because of its high cost and low functional importance, which let us make changes without affecting the overall assembly that much again. And we focused on these guidelines below. We'll discuss further in these following slides. So starting with the drill axle, we first removed the surface patches so the part was easier to handle, and this also makes it easier to orient and insert the part when assembling. We next increased the part symmetry so that it doesn't require a specific orientation, and we did this by adding that hole to both sides and putting those slots on the same sides, on both sides. So the final redesigned part has an emphasis on simple symmetry that facilitates orientation and makes it easier to insert it into our assembly. Moving on to our left body of the drill. So shown in the circles here, we changed that shell by reducing the complexity in side poles, as well as incorporating snap fits. We reduced the amount of parts by getting rid of all the fasteners and switching them out for snap fits. This makes the assembly of the drill much quicker. And we also highlight the decrease of part complexity here and a couple of key areas, which will be a large help for DFM. So moving on to our parts analysis, the drill axle redesign should have little to no functional impact while improving the assembly cost through symmetry. It's about 0.37 seconds quicker to assemble this part now, which can save around $61,666 in a year, assuming $60 per hour for pay. Redesign the body shell will also not have any functional impact because it's purely aesthetic and contributes to the packaging, doesn't change the function of the drill. This improves manufacturing costs by decreasing the complexity and makes it about 4 seconds quicker to assemble without fasteners. That'll save about $666,666 a year, assuming that same hourly pay.
Moving on to the design for assembly automatic, we chose to look at the chuck outer, the torque selector, and the torque adjust spacer as the three parts we analyzed. From these parts, we look to see a reduction in cost from $0.594 per item per drill to $0.438, with just a change in the injection molding and combining the two parts means that there's no more need for a metal spacer. On the torque adjuster knob and spacer, we increased part symmetry and reduced the total number of part counts by assembling these two parts, allowing it to now have a higher degree of beta rotation in assembly. And for the chuck outer, we increased the ease of insertion by adding a chamfer so that it can easily be assembled.
For the process selection, we chose for the parts that we redesigned for manual assembly. Starting off with the drill axle, the key dimensions for this part include the hole for which it connects to the other parts. And for the process selection for this part, we thought that this part was important because according to the function component mapping matrix, it applies torque and controls torque, so it's important that we chose a good process. And components that were important in this were tolerance, which was 0.13 millimeters, which we chose based on the tolerance for a 3-axis milling, and all the process selections the process that we selected were machining over centrifugal casting, because machining is a more commonly used manufacturing process that will be best used to manufacture 1 million batch size. And then the next part we chose was the left body, for which this part is key in softening grip. And the key dimensions for this is the thickness, which for machining we want to make sure that it's like not too thick to machine. And then the process selections for this, the key dimensions, the tolerance 0.1 millimeters, which we chose based on the tolerance for injection molding. And from the process selection, which the two processes that passed were machining and injection molding, and we chose injection molding because of the batch size. It would be easier, although both of them can surpass 1 million batch size. We selected injection molding because using a die for this process would be better.
So we did some DfM analysis and optimization on a couple of parts. The first of which is the drill axle, which again is the interface between the truck jaw and the gearbox. This part was improved by following the machining design guidelines by using a standard stock diameter, avoiding flat bottom holes to be able to use a drill bit, and minimizing tool changes and setups by optimizing the outer diameter geometry. The analysis in DfM Pro shows only sharp internal corners as a recommendation. This, however, must be kept as it is a crucial geometry for the part functionality. Here's the cost analysis for the drill axle's DfM changes. As you can see, the cost was reduced significantly in both methods of analysis, which were the hand cost analysis taught in class, as well as the Hub's online manufacturing service, where we have extrapolated the cost with a 20% profit for the Hub service. The next part is the body shell, which acts as a surface and mounting for many of the components. The design simplifies its geometry by reducing the amount of distinct faces and follows the injection molding design guidelines by keeping uniform wall thickness, avoiding side pulls, and integrating fasteners into snap fits. The DfM Pro analysis returned a number of recommendations, but due to the high complexity of the part and a failure in the SolidWorks' feature recognition, we weren't able to remove all of these in the 3D model. But if we were given a proper CAD where we could alter these, we would remove them. Finally, through the cost analysis technique for injection molding, we can see that the cost of the body part was reduced by about 10%, which could also be expected for the other half of the body shell.
Thanks, Ben. So now moving on to the product service systems, or our proposed ones for this product. So given the large volume nature of the product being produced, both the environment and the customer base could benefit greatly from the use of product service systems. So some proposed services that we have here for the hand drill include end-of-life recycling, tool rental options, and repair services. Recycling could allow for the reduction of waste materials in landfill. Tool rentals allow for the communal use of the tool, as well as customers only paying for by the job basis. And lastly, repair services could increase the longevity and utility of purchase drills. So now moving forward onto the impacts of these services. The environment could potentially benefit greatly since there will be less waste winding up the landfills due to consistent or the tooling could be used for longer due to consistent repair and proper end-of-life handling. And in addition to this, greenhouse gas emissions and energy usage would decrease since less overall products would have to be manufactured due to commonized use. And for customers, they benefit financially since they will only be paying for the amount that they use for the tool rather than the outright cost of it, as well as saving money through repairs and using the tools for longer. So moving forward to the summary, given the modifications that we've made, we were able to successfully reduce the overall assembly times and cost of the modified parts. Although some critiques we have identified for our design proposal include attempting more of a top-down redesign rather than simple modifications, as well as remedying identified issues in DfM Pro. Thank you very much.